Thank you. So, well, thank you, Diego. Thank you all for coming out. So for those of you who are part of the Galileo Galilei Institute, the school, enjoy the drinks. And for those of you in the community, I look forward to this opportunity to tell you a little bit about what's happening at the intersection of fundamental physics and machine learning. The title of my talk is Deep Learning plus Deep Thinking equals a Deeper Understanding. And that actually started off as a joke when I was encountering machine learning for the first time. And my friends were getting really excited about the way that machines could revolutionize our understanding of the universe. And I said, okay, you can do all your deep learning, but I'm a theoretical physicist. What I do instead is I do deep thinking. And I was very dismissive of this idea that we could actually use machine intelligence to try to understand our universe. And now that joke has turned into the tagline or the title of this talk here, that I really think that these type of techniques that I'll talk about can help us gain a deeper understanding, both a deeper understanding of fundamental physics, but also a deeper understanding of this technology that's changing society. And you know, every time you look at the news, there's something about artificial intelligence. And I want you to at least get a sense of what someone who works as a scientist, how I think about machine learning and how I think about the way that it affects my scientific field, and be happy to talk to you. But oh, a little bit closer, sorry. And happy to talk to you also about what the implications might be society-wise. So I've been to Florence a number of times. Last time I gave lectures, these are some of the photos of this wonderful city. And you can see me standing in line to get the Lamprodotto, which is delicious, of course. And this was back in January of 2020, when I was already starting to realize that machine learning was going to change my field. And in fact, as I'll say in a moment, just a few months later, I became director of this institute, the Institute for Artificial Intelligence and Fundamental Interactions, that has become a bigger and bigger part of my life. So what I'm going to be doing is I'm going to be first just giving you an advertisement for this AI Institute. I'm a professor at MIT. I happen to be on sabbatical in Paris for this year, but most of the time I spend in the Boston area, and tell you about this institute. And then try to explain my own personal journey into this world and try to justify why I've now become an enthusiast for these machine learning techniques. And then to complement the lectures that I'll be giving up on the hill. In particular, the students know that the title of my lecture on Thursday is the same thing, Jets in Space. I'll try to bring it down the hill and try to explain a little bit to you about a particularly interesting area that has some pretty pictures associated with it that maybe you wouldn't have thought would come from AI, but indeed was inspired by some of these AI developments. So let me start just by telling you about this institute. Which is bringing people together with funding from the United States National Science Foundation to unify researchers first in the Boston area, but also a link to the rest of the world at MIT, Harvard, Northeastern, and Tufts universities. Launched in August of 2020, so just a few months after I was visiting Florence the last time, with this tagline of deep learning, that is this AI revolution, plus deep thinking, fundamental principles coming from physics, using that to gain a deeper understanding of our universe. And the thing that I've learned as director of this institute is something that I'm going to be trying to explain to you, a kind of a collision, if you'd like, between two fields that think about the world quite differently. You know, I was trained as a theoretical physicist. I do my pencil and paper calculations to try to understand the way the universe works. AI works in a very different way. And realizing that we need to synthesize these things together. And so this collision between physics and AI has resulted in this following philosophy that I have. That to meet the standards of scientific rigor and performance, we need to teach machines to think like a physicist. When you read about AI, you might have heard about hallucinating chatbots or the worry that AI might give you biased answers. Well, physicists think about uncertainty. We think about how we gain confidence in scientific results. And if we can teach machines to think like a physicist, we would teach machines to be more reliable in the way that they process information. So that's one aspect of my thinking about this union of physics and artificial intelligence. And that's the one that makes me feel warm and fuzzy. I feel like I can bring something with my physics training. I feel like I can bring something to our understanding of artificial intelligence systems. The flip side is harder to appreciate, which is that to fully capitalize on AI technologies, for us to advance our understanding of how the universe works, we also need to teach physicists how to think like a machine. And that there really are interesting new lessons. I mean, anytime you have a new technology, there's a new way of looking at the universe. And artificial intelligence is giving us this new technology, and we need to figure out how to leverage that. We need to change the way that we educate our students. We need to change the way that we do research. And that is part of my own journey to get away from the pencil and paper and get more towards the computer and keyboard and eventually AI chatbots and things, incorporating that into my research. And those things coming together is what I would call centaur science. So the centaur is, of course, the mythical Greek creature that is half human and half beast. You can ask whether the human part is the physicist part and the beast is AI, or vice versa. Okay, but it's a synthesis of different ways of thinking, giving rise to a creature that is more powerful than each of those individually. And the challenge is this balance between knowledge about the universe that we get from physical thinking and knowledge about the universe that we get from these AI technologies. And there's this wonderful cartoon that I'm going to show you on the next slide that really highlights the challenge that I feel as a researcher trying to balance these two things. And so this is a cartoon that was shown to me. It comes from the New Yorker magazine. Kyle Kramer, who's a faculty member at University of Wisconsin at Madison, he's the person who showed me this cartoon. And I think it's a really wonderful way of capturing this spectrum. So this is the centaur scale. And on the one end of the spectrum, we can have not enough horse. That is, we could fail to actually capitalize on this new technology and fail to generate the kind of discoveries that we'd like in our field. On the other hand, we can have kind of too much horse, too sleek, right? But somehow finding this balance, finding the right amount of horse, the right balance between technology and physics knowledge, that's the thing that I strive for in my research. So let me show you just a couple of examples of finding that right amount of horse, finding this balance between it by highlighting some examples from the AI Institute that I direct. So the first example comes from actually my own former PhD student, who's now my colleague at MIT. So it's really wonderful to see the next generation rise up and embrace this challenge of incorporating machine learning into physics research. And so what she did is she took data, her name is Lina Nassib, and she took data from a satellite, the Gaia satellite, that's looking at the motion of essentially billions of stars in our own Milky Way, and trying to figure out whether any of the stars are moving in a weird way. And indeed, using AI system, she was able to identify that there was indeed some stars moving in kind of a dramatically different way than the way we expect. And that's going to be shown in this movie here, where we're going to see coming in from the left-hand side, you're going to see this kind of clump of stars, and that clump of stars is going to impact the plane of the Milky Way. And this is what you can infer by using a machine learning strategy to identify weird-looking stars and kind of run them backward in time and see where they came from. And so in this movie, you can see that we've inferred that this kind of blob comes and smashes into the Milky Way. I'll run that movie again in a second. This is what this machine learning algorithm seems to suggest. And it's very strange for these rogue stars to come and collide with the galactic plane. And what she was able to infer through a combination of studying the data and simulations of our own galaxy was that this is actually a clump of stars that are actually associated with this mysterious substance called dark matter. That what you really have is a bigger clump of dark matter. The stars are decorating on top of it, and it's that dark matter lump that is actually coming and hitting our Milky Way. And again, through a combination of machine learning strategies, physics knowledge, simulating our universe, she was able to infer that that was there. And she called this lump of stars, she called it Nyx, which is the Greek name for the goddess of the night, associated with the dark matter nature of this clump of stars. Another example, which kind of goes a little bit more in the opposite direction, is to think about AI systems as if they were physical systems and trying to use a language that physicists are familiar with for talking about the way that an AI system might operate. And so this is work that was led by my colleague Mike Williams. While I'm on sabbatical for this year, Mike Williams is the interim director of this institute, so I feel obligated to highlight his research on this slide. And what he did was study this very bizarre phenomena that can happen with AI systems, where an AI system, you can give it a task to solve, it tries to solve it, it tries to solve it, it tries to solve it, can't do it, but then suddenly it has an epiphany. Okay, this is kind of funny to think about a machine having this transition, a transition to knowledge. And what a physicist would call a phase transition, that we go from one phase, a phase from a gas of uncorrelated information, to this crystal of knowledge. And so what he was able to show is that for a particular type of math problem that the machine was trying to learn, you see these kind of numbers on the screen there. Those numbers, the machine is trying to figure out how to organize these numbers, can't figure out how to organize these numbers, doesn't understand what these numbers are, and then suddenly it crystallizes into this regular shape, this circle of knowledge associated with actually what we know about the way that numbers operate. And this is kind of an amazing realization. In the machine learning literature, this is called grokking. This is when you have a sudden epiphany appearing from a machine learning system. And again, Mike and collaborators were able to show that this really is the way that, like, for example, you have a bunch of molecules that crystallize into a regular structure. He was able to show that that's the way the AI system worked. So that's a way of using physics language to understand AI. But you can also go the other way around. So now that you know that you have this crystal of knowledge that AI systems can generate, maybe we should release it on even more complicated systems. And so Mike is a nuclear physicist by training. And so he said, well, maybe I can try to use it to understand nuclear physics data. And what he was able to show is that the machine didn't give you a circle in the case of nuclear physics data. It gave you this spiral structure. That's what the machine kind of found. Its crystal was more this like helical, almost double helical DNA-like structure to it. And the thing that the machine had identified both corresponded in certain cases to existing human knowledge about the way that nuclear physics works, but also had new insights that turned out to be better than any existing human way of organizing information. And so this ability to predict physical systems using this knowledge about the way AI systems work has been this wonderful loop between physics and AI, combining physics intelligence with machine intelligence. And so for the rest of this lecture, I want to give you an example like this, but from my own research, and trying to explain to you a problem that changed my mind, a problem where I thought that AI was exactly the wrong answer to the problem, and then it turned out to be, in some sense, the right answer and generated knowledge for me. And I want to try to explain that. And it's a complicated story involving a bunch of different cute little pictures that I'll try to explain to you with a huge number of, well, huge by theoretical physics standards. Okay, so having 7 collaborators contributing to this. This is large for a theoretical physics collaboration. Multiple machine learning algorithms, thorny problems in physics, and contributions from amazing early career talent. And part of why it's so fun for me to be at GGI lecturing this week is to also interact with the students here who are the next generation of talent in this area and communicating whatever I know about my own field to try to help the next generation go even beyond what I've and my collaborators have been able to do. So this is what I'm going to try to explain to you. But just to summarize this first part of this talk, that we're seeing these advances both in AI and in physics at the same time, driven by centaur scientists, early career researchers who have found the right amount of horse, the right amount of balance between these two different ways of thinking. Okay, so now I want to talk about my own AI journey and kind of what happened to me. How did I go from making jokes about deep learning and deep thinking to really embracing both of these as ways of understanding the universe? And it started back in fall of 2016 when I was very much an AI curmudgeon. And 2 graduate students walked into my office at MIT. Their names were Patrick Kamitsky and Eric Metodiev. And they were very proud. They had done their master's thesis research using convolutional neural networks, which is a particular type of AI system that's really good at processing images. And they used it to understand a particle physics problem that I'm going to try to explain to you, having to do with quarks and gluons. And what they said is that they could run their AI system and very confidently tell you whether a collection of particles was associated with a quark and a collection of particles was associated with a gluon. They were very proud of their work. Their work was even published. And I, being in AI curmudgeon mode, as we would say in the U.S., we would say, get off my lawn. I don't like these AI systems. That's not the way that we do theoretical physics. And more particularly, my response to them was, what do you even mean by quarks and gluons? And what Patrick and Eric couldn't have known is that at the same time as they were writing their paper using AI, I was writing a paper saying why this whole problem that they were trying to solve was ill-posed, that it was just didn't make sense from a theoretical physics perspective, and that people needed to rethink the problem. And indeed, we do need to rethink the problem. It just happens to be that the answer is not less AI, but more AI, more artificial intelligence to help us with physics intelligence. So this is the problem that I need to explain to you. So I need to explain to you the problem, which itself is a little bit technical, try to tell you where the solution comes from, which is a little bit technical, and try to do this in a way that is more or less entertaining. If you find it not entertaining, you can, of course, go to the bar. I have my own Spritz in hand, just in case it goes really bad. Okay, but I'm going to do my best to try to explain what this is and maybe teach you a little bit of physics along the way. So I am a particle physicist, and we think we understand what the fundamental particles of the universe are. And this is encoded in a theory that's called the standard model of particle physics. And if people have encountered the standard model, they might have seen this graphic, which is showing the fundamental ingredients of our universe. In orange are particles that we call quarks, which will be in part of this story. In green, we have particles that are called leptons. In blue, we have the force carriers of the standard model. And at the center of the standard model, the Higgs boson, which was discovered at 2012 at the Large Hadron Collider at CERN. And this picture is a graphical representation of our knowledge about fundamental physics. And if you look at this picture, you might say, oh, so it must be that you're intimate friends with all of these particles, that you've encountered them in your day-to-day life. And the answer is definitely not. Actually, very few of these fundamental ingredients are ones that we've ever seen directly. The only ones that we really can see from this pie chart are the ones that carry the electromagnetic interaction. So, of course, there's the electron, which is responsible for electricity. The photon, which is the particle that carries light. So electrons and photons are pretty important to us just in this room right now. There's another heavier cousin of the electron called the muon. And these are the only ingredients from the standard model which I could really say I can hold them, feel them, touch them directly. Everything else in that pie chart is something that I had to infer. I don't have direct evidence for it. And machine learning turns out to be a really good way of inferring information, even if you can't see it directly, which maybe explains why machine learning is so important for physics applications. Everything else in that pie chart you can't see directly. So the last time I was in Florence giving lectures, I was giving lectures about quarks and gluons. Quarks and gluons experience the strong force, and the strong force is so strong that it binds quarks and gluons together to make composite states. So I take a bunch of quarks, stick them together, and that gives rise to a zoo of particles, of which the most famous ones of them are the proton and the neutron, which are the center of atomic nuclei. And then some of those other particles there, the Higgs boson, W boson, Z boson, top quark, tau lepton, like those, essentially you make them, they immediately disintegrate, so you can't see them directly. Neutrinos are these ghostly particles that sail through everything, so you can only infer that they're there because of their absence. Somehow, from the very little information that we can actually see directly, we're supposed to infer what the underlying structure of the universe is. But the thing that I want you to come away is to say, Patrick and Eric were saying, I can tell the difference between quarks and gluons, and I can say, you can't see quarks and gluons. They're bound together by the strong force. What do you even mean by a quark or a gluon? You can never hold one in your hand. You can't see it directly. So let me tell you that same story. It's actually, there's one more ingredient, which is that this makes it look easy. because I'm a theoretical physicist, my experimental colleagues actually have to deal with messes of data that look like this. So they don't even get particles coming out with names attached to them. They have a bunch of different sensors that are trying to synthesize a lot of information, essentially like a megapixel camera every 25 nanoseconds trying to take pictures of these collisions that are constantly happening and trying to decipher that mountain of data. The particular area that I work on are these sprays of particles called jets. And we're going to be experiencing some of these jets in the rest of this talk. Jets themselves are manifestations of quarks and gluons. When I see a jet, it probably came from a quark or gluon, but it's not a quark or gluon directly. It's a manifestation, it's an echo of a quark or a gluon, but it's not a quark or gluon directly. And so we're going to be studying these jets and processing these jets, but we have to remember that a jet doesn't come and say, hi, I'm a quark jet, hi, I'm a gluon jet. It's just, I'm a collection of particles, and good luck figuring out where I came from. And that's the challenge that machine learning is trying to help us with. So let me tell this same story in movie form. So this dot here represents a bundle of protons that are being accelerated at the Large Hadron Collider outside of Geneva, being sequentially accelerated around the rings at CERN. This ring here, the SPS, is where the W and Z bosons were discovered in the 80s, but that's just the injector now for the bigger Large Hadron Collider, which has 4 different collision points. And now we're going to be going underground, 100 meters underground. The standard model of particle physics and equations is on the wall. This blue tube are superconducting magnets to bend the protons. We're going from the Swiss-French border here. And in a moment, we're going to be going inside the proton. And you can see that's a visual representation of quarks and gluons bound together. But of course, they can't be liberated. And we're trying to understand those quarks and gluons. But they're, again, bound up all together. So as a theoretical physicist, there is this amazing moment in time when really I'm living in the world of quarks and gluons. Like those are the real ingredients. And if I could go to that instant and zoom in, I would really be able to see a quark or see a gluon. It would have a reality to it. But sadly, that's not the world that I get to detect. I can only see the echoes of those particles. I only see these sprays of particles coming out. And somehow I'm supposed to figure out how the universe behaves at its fundamental level from this very messy collision data. And that is indeed the role of physics. And we've often had this challenge that we have data, the data is complicated, and then we have to figure out how the universe works from that complicated data. And machine learning is one of those strategies that can help us with that. So there's one technical ingredient that I need to tell you about, which will help me for one of the last plots that I show in this talk, is just a technical point about one fact about how quarks and gluons operate. There's in literature, there's this idea of Chekhov's gun, where if you have a multi-act play and you kind of plant a pistol in one act, then it must go off in the second act. And so here we not have Chekhov's gun, but Chekhov's gluon. So at the end of the talk, there will be the smoking gun here. That there's a fact that I'm just telling you that quarks and gluons, when you make them, they radiate, that is, they generate additional particles, proportional to their color charge. So electric charge is something we're familiar with. Electrons have negative charge, protons have positive charge. The strong force is associated with something that physicists delightfully call color. And the amount of color charge is associated with how much radiation is made, basically how many additional particles are made. And quarks happen to have a charge of 4/3 and gluons have a charge of 3. And their ratio is 9/4, so that's math that probably everyone in this room can do. And that number 9/4 is also going to be a number that the machine is going to discover for itself. And I fell out of my chair when the machine came up with the number of 9/4 because I didn't tell it that information. It was able to figure that out by the particular data processing that I'll describe. Okay, so that's the challenge. So Patrick and Eric come into my office. They say, we're going to try to tell the difference between quarks and gluons. I tell them quarks and gluons are not well defined. And now, if we're going to be a centaur scientist and try to tackle this problem, we need to both think like a machine and think like a physicist. And that's the challenge, is how do you incorporate these two different styles of thinking? So one direction is going to teach the machine about a physics fact. And the physics fact that is super important is that energy is conserved. Anytime you've encountered a physics system, there's conservation of energy at work. We teach this to all of our students in physics university classes. And so I now need to teach the machine about this fact of energy conservation. And we're going to see on the next slide a psychedelic image, which is looking inside of a machine learning architecture after I've taught it about energy conservation. And it's going to respond by saying, OK, you've taught me about energy conservation. Let me tell you something interesting about the structure of your problem. And it's going to give it to me in this psychedelic image. That's what's going to be on the next slide. So this is thinking like a physicist, telling about energy, or in particular, the flow of energy. And OK, those equations aren't necessarily all that important, just to show you that there really is a kind of equations behind this. This is what a machine interprets when it looks at particle physics data. It looks at particle physics data and it turns this into this psychedelic collection of the kind of rings. And what the machine is trying to tell us is that it's trying to tell us that it thinks that information, these rings are representing where it thinks the information is, and the tighter rings at the center are telling you that the machine thinks that there's a lot of information at the center of these sprays of particles, these jets, and the bigger rings on the outside are telling you that it thinks that there's less information on the periphery. This turns out to be very closely related to things that I could do pencil and paper calculations about. But I didn't tell the machine that. I just told it about energy conservation. It responded by giving me not only a beautiful visualization of what it dreams of when it dreams of jets, but also responds in a way that gives me some confidence that the machine has actually learned essential physics knowledge. So teaching a machine to think like a physicist. If I teach the machine about energy conservation, I have an interpretable, what we call the latent space, an internal representation of physics information in a way that is valuable to the machine and something that I can actually understand why it's making that decision. So again, this is the direction that makes me feel warm and fuzzy. I feel like, oh yes, I'm using my physics knowledge to make AI systems that are more reliable and interpretable. The flip side, though, also I have to think myself. I need to now think like a machine. I'm a physicist, and I need to think about, wait a second, I told you about this problem that I don't know what a quark is or I don't know what a gluon is. How could I possibly define even quarks and gluons when they're all bound together? How do I pull them apart? How do I separate those concepts? And this is where you had to go into the machine learning literature and try to find other examples in the literature where people have faced this problem, where they have a lot of data. This data is convoluted and messy, and you want to disentangle it. You want to separate it into its component pieces. And so this is the other direction, teaching myself to think like a machine. And actually, the lesson here comes from the world of language processing, that if I give you a library of information, and I tell you to, for example, build a card catalog for that library, this is an arduous task if you as the human has to go through every single book. But what you can do is you can throw a machine learning algorithm at it, and that machine learning algorithm can analyze the types of words that appear in all those books, and I can actually categorize them into topics, that is, into conceptual groups where the words are kind of all associated to each other if they come from documents of the same type. So this is a particular example coming from genetics, where you have a bunch of genetics papers. And the topics, for example, there's one topic associated with the words gene and DNA and genetics. Those are clearly genetics topics. But then there's also things in evolution, the words like life and evolve and organism, or things in neuroscience, brain, neuron, nerve, or things in data science, data, number, computer. And these algorithms, these so-called topic modeling algorithms, are able to figure out from a collection of documents what the word clouds are, and you can basically take monstrously messy data and distill them into their component pieces. And so that's essentially, with this idea, this is essentially what we were able to do with quarks and gluons. We were able to say, I'm going to take a lot of messy data from a collider, and to use this algorithm, I need to come up with a vocabulary. So I need to have a machine come up with the idea of what words are associated with my data. And then I can use this particular algorithm to then separate those words into piles associated with, in this case, just two topics, the quark topic and the gluon topic. And that indeed is a way of processing data such that I can learn about the underlying components, even though I can't separate them out directly. I can't have an article that's just all words just from one category. All the categories are mixed together, yet this machine learning strategy is able to disentangle the pieces. So I'm not going to explain to you how this technically works. I'm just going to show you a cute picture of a koala and then a graphic that's showing particle physics data as if it were a bunch of documents. So this koala is a technique. Okay, physicists are known for their acronyms. So CWOLA, pronounced koala, stands for classification without labels. This is one of the most torturous acronyms that I've ever done in my career. But anyway, you have a koala, but that koala is reading a book because it's learning about natural language and applying that to particle physics data. And then I can make documents out of particle physics data. And then I can just do the algorithm from the previous slide. So, I mean, this sentence is perhaps no better than the actual technical wording that you would use. But I'm defining quark jets and gluon jets as the vocabularies resulting from this algorithm. That's about as close as I can get to technically explaining what we're doing. But this analogy, hopefully with natural language, is a little bit helpful. That the machine can both, with those rubber bands and those rings, we're basically defining the words of the problem, using that information, turning it into documents, then using well-established machine learning strategies and accomplishing something that I didn't think was possible. Defining quarks and gluons, that's what Patrick and Eric said that they wanted to do when they came into my office, and we succeeded. Okay? And I was so over the moon that we were able to do this that when Dennis Overby of the New York Times called me up when our AI Institute was launched, so this was in 2020, in November of 2020, I went kind of over the top extreme when Dennis Overby said, hey, could a computer actually discover or devise a theory of everything? Could you imagine having a machine process all the knowledge that we have already about physics and chemistry and whatnot and come up with a theory that describes all known phenomena? And so this is me as quoted in the New York Times, a little bit over enthusiastically. Again, having just done this one simple quark-gluon problem, somehow I extrapolated and I said the following. I said, in 5 to 10 years from now, I'm going to want to do exactly what you're getting at. Here's the data. Here's a very rough toolkit. Find the equation I could put on a t-shirt, the equation that replaces that standard model of particle physics that I showed you before. What's the equation that replaces Einstein's general relativity? And my friends made fun of me, right? Because, come on, Jesse, you've kind of gone off the deep end. There's no possible way that a machine could do that. Well, this article was from November of 2020. 2 years later, ChatGPT was announced. And then the conversation was completely different. Because now you started to have an AI chatbot that was able to ingest monstrous amounts of information. And then people would say, Jesse, why haven't you done it already? Why haven't you already fed all the knowledge, human knowledge, into an AI chatbot and ask it what the theory of the universe is? And indeed, people are trying to do that. But I think our conversation has now changed now that we've seen these advanced AI systems process monstrous amounts of data in almost human ways. We really are starting to raise our ambitions about what we want to do in the sciences. But my transition, the thing I just showed you here, was taking a completely well-defined science problem that I did not know how to solve using ordinary traditional physics techniques, but with insights from the artificial intelligence literature, was able to solve to my satisfaction, so much so that now this is the way that I think about the problem myself. I think about quarks and gluons in the same way that I think about vocabularies and text processing, and it's really changed the way that I think about my physics. So kind of the summary of this part of the talk is this idea of fusing the power of AI with insights from physics, and hopefully you've gotten a little bit of a sense of why I'm so enthusiastic about this intersection, because it really changed the way that I think about my own research problems. So the last thing that I want to do is maybe just for fun, just to show you some more pretty pictures, and say you a little bit more about these jets. And this is the kind of the part of the talk where the pictures are pretty, and it's challenging because particle physics data, it's hard to make pictures of it. It's hard to show it. It's very abstract. And this is also going to be abstract, but abstract in a different way, and hopefully it's at least entertaining, the kind of pictures that I can draw with help from machine learning. So the standard way that I would draw a picture of a jet is I would just make a picture of how these particles look like in a detector. So here's these sprays of particles going around, but actually, each of these individual sprays of particles actually doesn't carry much information. I need to synthesize a lot of data using machine learning to disentangle and figure out what's going on. And as I said already, a single jet carries essentially no information by itself, but I can define quark jets and gluon jets as these kind of categories, these vocabularies. And now I want to try to show what these vocabularies look like. And again, it makes your brain hurt to try to imagine trying to do this visualization, so I'll do my best. So we had this the dichotomy before about thinking like a physicist, teaching machines to think like a physicist, or teaching machines to think like a physicist, or physicists to think like a machine. The era of AI is the era of interdisciplinary connections, where you start grabbing ideas from wherever you can get inspiration from. So the next slide is entirely a joke. So we didn't actually get inspiration from this, but I'm using a joke as a way to avoid trying to explain the real problem. And the joke is that we're going to be thinking like an American poet. It's like, okay, how could poetry possibly be relevant for physics? And indeed, in this case, it's not so relevant for the science, but it's relevant for telling a joke. When I'm processing data and I'm thinking about experimental data is really messy, and I need to clean up that data. And the technical term that we use in physics for when I'm cleaning up data, we call it unfolding. And if I want to unfold all my detector effects for everything, everywhere, all at once, then you'd want to call this omnifold. Omni, everywhere, folding, fixing everything up. And there's a particular graphic here that's showing you a particular algorithm using AI to do that correction. But the joke here is both the logo and the name Omnifold, because that's not from us. Omnifold comes from the American poet Emily Dickinson. Emily Dickinson's poem number 975, "The mountain sat upon the plain in his tremendous chair, his observation omnifold, his inquest everywhere." And so the OF for the Omnifold logo is, of course, the sun rising behind a mountain, inspired by Emily Dickinson to name this particular algorithm after that poem. Okay, so again, this is just an excuse not to have to tell you about the technical details about how you clean up the data that you're faced with. The other interdisciplinary connection, which is wonderful for me personally, because right now I'm on sabbatical in Paris, away from the Boston area for a year, and a bunch of the streets in Paris are named for a French mathematician. That mathematician's name is Monge. And if I want to think like a French mathematician, back in the 1780s, Monge was thinking about the problem. And unfortunately, my French is probably, well, as bad as my Italian. But the theory des Deblais et des Rombley, okay? And this is actually a monumental paper having to do with what looks like a very prosaic problem. So Deblais and Rombley is just the name for essentially a pile of dirt and where that dirt's going to move to. And so you can imagine in the 1780s that you would want to move dirt around to make trenches and embankments, and you would like to do that in the most efficient way possible. And Monge plus research coming over of the subsequent centuries turned this into an amazing mathematical framework called optimal transport, the optimal way of moving stuff around, whatever that stuff is. So you can move dirt around, you can move, when you get deliveries to your home, someone has solved an optimal transport problem to make sure that the delivery vans are doing in the most optimal way to move things around. Or you can move energy around in a particle physics detector, and that is also a type of movement that you can do, a geometry that you can define. You replace dirt with energy, and then goes from what's called the Earth mover's distance, which is the way that computer graphics people talk about solving this moving of, in that case, pixels around, to an energy mover's distance that I'll show you on the next slide, of moving energy around in a collider context. And so what you can do is you can kind of take all those jets that I showed you before and then talk about how similar jets are by how easy or difficult it is to kind of morph the energy from one jet and turn it into another one. Okay, so in this graphic here, what you're seeing is you're seeing three jets. Each of these jets is some kind of spray of radiation or spray of energy. And then here I'm showing you how much work, someone is like taking a shovel and grabbing amount of energy, moving it to another place to make one jet look like another. The amount of work that you have to do is a way of defining a geometry, a notion of distance, and that from that notion of distance, you can now create a whole space of jets where you can try to imagine placing jets in some geometric space so that the distance between those jets corresponds to how similar they are by this measure. And already, kind of, even if you're a practicing physicist and understand the technical details, your brain is already starting to hurt. You're saying, wait a second, jets are energy, I'm moving energy around, energy defines distances, and I'm supposed to think about geometry as defined by the distances between jets. Your brain really hurts, and then you take a sip of your Spritz, okay? But this is really what's going on, and this is actually a beautiful way of actually organizing information. And you can start to make pictures of a data set that it was very hard to visualize, and this visualization that I'll show you on the next slide, okay, it's beautiful by particle physics standards, maybe not by the aesthetic standards of the city of Florence. But what we have is we have a picture here where we have both the forest and the trees being shown at the same time. That gray blob there is like the forest. These are a bunch of jets, and I'm showing kind of the overall canopy. But then I'm showing you the trees. I'm showing you individual jets, and their distance from each other shows you how similar they are. So the jets that are color-coded in blue, they're very kind of pointy and prongy. The ones that are color-coded in red kind of have these actually two prongs of radiation. And I can start to visualize and gain intuition about this about the space. And I've stared at many of these type of plots. And the main deficiency of this particular representation is that it's on a slide. It's in 2 dimensions. And the challenge that I'm now going to try to explain to you, and that we'll conclude with, is, well, actually, this space of jets, it's not a space that I can easily project onto 2 dimensions. This is an abstract space that lives in, well, what dimensionality does it live in? And that's the science question that we'll come to for the end of this talk. Okay, so let me just try to summarize where we are, because we've covered a lot of ground. I've told you something about quarks and gluons and the strong force. If you've learned nothing from this is that there is this force that's called the strong force, and you've never heard about it before because, well, it binds everything together, binds quarks and gluons together, and so it has no impact on our day-to-day lives. But through decades of study, we've convinced ourselves that this really is, in the microscopic world, a fundamental force of nature, the strong force involving quarks and gluons. We've confronted it with public collider data. So I didn't emphasize this fact, but the pictures that I've been showing you have been based on public data from the Large Hadron Collider. You could go and download this data yourself. It's a resource for humanity, and you could make the same type of pictures that I made. And this idea of open science and open source science is really important for the public to gain trust in scientific understanding. I have corrected that data for detector effects using Emily Dickinson's help with Omnifold. And then I've done this crazy thing involving a koala, a psychedelic image, and a stack of papers where I've disentangled, okay, this is now the technical term for what I said before, I've disentangled using weak supervision on set-based classifiers with topic modeling. So that's what I would say in the abstract of a paper that I'd submit to a physics journal. But really it's cute koalas, psychedelic images, and documents made out of quarks and gluons. And then I've triangulated it with the help of Monge and moving dirt around from the 1780s, right? All of this, at some level, is still under this banner of AI plus physics. Physics knowledge at one end, various AI strategies at the other end. It's this amazing spectrum of techniques, and all of them are going to come together in the very end. Okay. So the last thing I'm going to show you is a plot from a science paper, which, again, I find amazing to me, where I'm going to try to say this space, this abstract space that I'm trying to show you, the space of quark jets and gluon jets, what's its dimensionality? So you can ask the same question, what's the dimensionality of all you in this room? And you say, well, geez, I'm living in 3 dimensions. Well, actually, yeah, you are 3-dimensional creatures. But actually, you in this room, you're 2-dimensional. Why? Because you're all lying in a plane here. You're not stacked up towards the ceiling. And in particular, the number of neighbors that you have, as you would zoom out, you shake the hands of your neighbors, the number of neighbors that you have grows in the same way that the areas of circles would grow as you went out. And that's the way you would say you're 2-dimensional. So now you can ask the same thing about quarks and gluons. Quarks and gluons, they have kind of friends nearby, and how many friends do they have as you go out and out and out? And the growth of the number of friends that you have is a way of trying to figure out the dimensionality of that space. And so here's the plot of the dimensionality of the space, and it's a plot because actually jets are complicated. Jets are these really hard to visualize because they're actually complicated objects. If I were to go to that moment in the movie where I freeze the frame, jets are zero-dimensional. They're just a dot, a single quark, a single gluon. That's all it is. But as I zoom out, I get more and more and more information. The dimensionality grows, 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 and it grows in this superfractal way. So fractals are objects that if I zoom in or out on it, they look self-similar, they look the same. Quarks and gluons are systems that if I zoom out, I get more and more and more and more information. Again, this is all coming from a collection of a bunch of machine learning algorithms, but because I'm a theoretical physicist, there's actually two different things being shown here. The solid curve is all the machine learning, and then of course, being a theoretical physicist, I put the dash curve in there, which is a theory prediction for what these things should look like. So as a theorist, I'm really excited that the dashed lines and the solid lines overlap, so that's really great. But then why do I have three sets of colors? Why do I have red and blue and purple? Well, red is gluons. How many friends do gluons have? Blue is quarks. How many friends do quarks have as I zoom out? And then you can ask the same thing, kind of complementary, like a quark, how many gluon friends does it have? Gluons, how many quark friends you have? Hopefully that's symmetric, that who you're friends with, you're also friends with. Okay. This plot here is, again, made me fall out of my chair as a theoretical physicist because the fact that these curves are all different is saying that the machine had figured out, by using all these machine learning algorithms, the machine had figured out, in some sense, the intrinsic fundamental thing that distinguishes quarks from gluons, which is their color charge. And if I take the ratio of the red curve and the blue curve, I get this green curve here. And the green curve is now this kind of Chekhov's gluon, this 9/4. I did not tell it about 9/4. I just said, throw this machine learning processing on it, and out popped this as an answer to that question. And of course, we already knew about quarks and gluons. Nobel Prizes had already been awarded for that concept. But had it not been, then you can imagine some graduate student processing public data, doing this kind of topic modeling thing, and then discovering, wait a second, why are these two categories whose growth in their superfractal dimension turns out to have the ratio that happens to be close to 9/4? And this is actually a case where the data does a little bit better than the theory. The data, which is this kind of wiggly line here, is actually closer to 9/4 than the theory prediction. And that's because there's actually a kind of a bug in the theory prediction that causes it to get a little bit distorted. And the fact that 9/4 is more reliably extracted from the data is actually kind of an exciting thing. So this is an example in action of deep thinking about the structure of the universe. Fundamental numbers. 9/4 is a fundamental quantity, a concept in our universe, via a variety of deep learning strategies, again, using the help of a bunch of interdisciplinary connections. So the era of AI plus science is the era of these cross-disciplinary connections, and part of what makes it so exciting for me to be part of the community of people thinking about it is that I get to pull in strategies from a bunch of different fields, and it's wonderful for me to have conversations with other scientists about what they're doing to process their data set. And also, if you have ideas, it'd be lovely to talk about those during Q&A in a moment. So let me summarize what I just told you, and then give AI the last word. Okay. So summarizing what I just told you, hopefully I've given you some sense that deep learning plus deep thinking really can give you a deeper understanding. That it's this next generation of early career centaur scientists that are leading this way in AI plus physics. That we're able to fuse the power of AI with insights coming from physics, and that these cross-disciplinary connections can give us new opportunities to process our data and visualize our data. And hopefully these cross-disciplinary connections will also influence the way that AI systems are developed in society more generally. And having people who are thinking about science problems, that's a wonderful, more or less low-risk sandbox to play with these AI systems in a way that hopefully we can make them more robust for societal applications. So as I said, I'm going to give the AI the last word. So I mentioned before, wanting to hand a bunch of basically asking an AI chatbot, give it a bunch of information, and maybe spit out a theory of everything about the universe. But this actually turns out to be not so far-fetched in that you can actually take trusted documents, have those documents be synthesized by an AI agent, and then have a way of interacting with that AI agent and gain insights. And one of the things that was done was an April Fool's joke on my behalf. So in April of 2023, a bunch of people at the AI Institute that I direct, they took ChatGPT, fed it all of my papers, my websites, and then gave it a colorful personality and generated something that's called ChatJessieT. So you can go right now to chatjessieT.com and ask it questions if I haven't answered this question in this talk today. So I'm not going to show you that from that, but actually a more interesting case is you can take scientists historically and ask them questions about their work. And so we took this to the Cambridge Science Festival, where we made an AI version of Marie Curie and fed it all of Marie Curie's insights, but also made sure that Curie didn't know, or the AI version of Curie didn't know, about anything happening after the time of her death. And we then watched what people at the Cambridge Science Festival, what questions that they might have for Curie. And here's one of the questions that came from one of the people at this festival. And both the question is interesting, and then also the answer, I think, is a nice way to end this, this talk. Okay, so this is Gaia Grosso, one of the postdoctoral fellows at IFI, with the same AI chatbot on the screen here. And this is a question that was asked by one of the participants because Gaia was talking about AI and science and federal funding. And so someone said, hey, Maria Curie, why is it important to fund AI and science? Of course, AI didn't exist at that time, so fascinating to know what at least the chatbot version of Curie would say. And so I'll just read this off, and this will be the end of the talk. So, why I'm not familiar with the concept of AI or artificial intelligence, as it is beyond my time, I can certainly speak to the importance of funding science. Science is the key to understanding the world around us. It is through scientific research that we have been able to make significant advancements in medicine, technology, and various other fields. In my own experience, it was through the generous funding of our research that my husband Pierre and I were able to discover the elements polonium and radium. This discovery not only expanded our understanding of atomic structure and radioactivity, but also led to the development of new treatments for cancer. Therefore, funding science is not just an investment in knowledge, but also an investment in the future of humanity. It allows us to push the boundaries of what we know and to improve the quality of life for all. As for AI, if it is a scientific field, I would presume that funding it would have similar benefits, allowing for advancements that could potentially benefit society in ways that we cannot yet imagine. And certainly that's the way that I feel about this technology that is both inspiring and scary and all those things all together. And hopefully I've given you a little bit of an insight about what a theoretical physicist thinks about this technology. And I look forward to taking any questions you might have. Thanks very much. Yes.
Regarding your last comment,
yes.
With the current administration, are your federal funds being confirmed?
Oh, so you don't know how close to home this is. So this is being recorded. So I will say things that are on the record. So our funding, you can go to the National Science Foundation website. We were started in August of 2020 for a 5-year grant. So you can add 5 years, right? So that gets us to August of 2025, which is exactly when my sabbatical started. So I was really hoping that I would secure renewed funding for our effort, and then I get to go on sabbatical. And we are in a fascinating state of limbo as basically trying to figure out how funding will work. I am optimistic. But I think this is an example of why, if we really want to have sustained progress internationally, we need to make sure we have sustained support for these type of efforts. And the uncertainty that comes from not knowing whether big grants are renewed or not is something that's a challenge. But we're doing our best. Of course, I'm at a place like MIT that can weather the storm better than other universities, but it is a challenging time. And I think the storytelling of saying that curiosity-driven research can both change the way that I think about my own problem, but then also extrapolate maybe to other areas and change the way that other people think about those problems. That's a story that we have to tell to try to secure renewed funding. But that is where we are right now. I would love to have been able to say, yes, and we're going to have another 5 years of this awesome science. At the moment, I'm hopeful of that. But sadly, given the recording, I cannot say anything more than that. Yeah. Yeah. Yes?
When you talked about the solution to problems, right? You said that you solved it in a way that you were satisfied about it.
Yes.
Could you elaborate more on what you mean by in general? In this case, I suppose that satisfied means that you found this ratio that people knew before.
Yeah.
But if you don't know the solution to the problem, and this is what we would like to do with AI, I guess, right? Finding solutions to problems that we don't know the answer for. How do you judge whether we found something or we didn't?
Right. So the question is, to repeat it, is, I describe myself as being personally satisfied by our solution in a way that has changed the way that I think about my problem. Are you satisfied? Are you satisfied by this answer? You may not be. And this is the dialogue that we have as scientists always about whether an explanation is one that is satisfying to us. And if you look at the history of science and think about how long did it take for various ideas to gain traction, it can take a long time for people to appreciate, oh, this is really the way that things work. In fact, there's a constant dialogue of understanding. And AI is now becoming a part of this. So for this particular case, for this particular problem, this is a problem that I convened a working group to try to address this problem. And I have slides from that working group discussion where I wrote down, this is pre-AI, I wrote down the definition that would satisfy me. And I wrote it down and I put it in a box and I said, this is what we need to aim for. And that was, again, pre-AI, my way of saying, having thought about this problem, what would satisfy me as a solution? And the reason why I'm satisfied is because AI provided almost exactly word for word that. Like it of course, didn't do that directly, but when I'm looking back and saying, oh, wow, one, I was pretty smart before. I knew how to define my problem in a way that would be scientifically satisfying if I could do it. And then later on had something that met that standard. And I think those are the cases where it may be the easiest. One thing that people often ask is, Jesse, when will other scientific disciplines have their AlphaFold moment? Why was AlphaFold so important? Why did we get Nobel Prizes? I skipped this slide for time. Why did we well, this is Hopfield and Hinton's Nobel Prize, but then the Nobel Prize for chemistry for protein folding. Why was that kind of immediately recognized? Is because the community had said, here is the problem. Here's what success looks like. Here's a definition of success. And then AI was able to deliver on that definition of success. So those are the cases which are maybe easy, where you've ahead of time decided what the standard is, and then you could see if AI can meet it or not. Of course, what we really want is want that moment of inspiration that changes our mind, that changes the way that we think about problems. But just like any time in science, when you have someone who comes with a new paradigm, it deserves scrutiny, and that's the dialogue that we always have to do when we're doing scientific research. And the number of times that I've had arguments with people about whether this really is or is not a solution to the problem, to what extent can I trust what I'm doing, those are fun conversations to have. I myself am convinced. Now the burden is on me to convince the community that this is the way that we should tackle these things. But it's no different than the ordinary messiness of the way that we come to scientific consensus. It's just that we now have a huge new toolkit at our disposal for addressing that dialogue. Yes? And you're specifically asking about particle physics? Yeah. So the question was, how do I foresee AI changing the way we do particle physics? Okay. And I would say that it changes potentially every single aspect of our endeavor, starting from when you design the experiment to begin with. So when you're designing an experiment, one of the things that you would like to do is you'd like to make sure that your experiment is safe, for example. safety means different things in the AI era. Because if you know that you're going to be deploying AI in the way that you're either running your experiment or processing your data, you actually need more safeguards, not less, to make sure that you're doing something that is both safe and trustable. And so you actually prioritize monitoring. You prioritize having experimental apparatuses that actually can give you more information, auxiliary information about what's going on. This, by the way, is also seen in robotics. With robotics, some of the really amazing things that robots are able to do are because they have many, many more sensors than you would have in older robotic systems. And the more and more sensors and the more sensitive those sensors are, the more reliable their operations are. But the way we design and build experiments, possibly even the way that we advocate for those experiments, the way we make projections about what those experiments will do, the way we collect the data, the way we store the data, the way we process the data, the way we interpret the data, all these things are now up for grabs. And it's the current generation's job to figure out how to navigate that. So for me personally, I find it challenging to use some of these AI systems because I was trained in an era where it was more pencil and paper. Or when I did coding, my first coding projects for particle physics were in Fortran. Well, okay, there are still people doing Fortran, but that's not the language that AI is usually written in. And so I find myself almost not able to keep up. And now you have these chatbot interfaces, and you're trying to figure out how do I actually do programming, but now in the new programming language is apparently English. So you type in English what you're trying to do. How do you actually get reliable outcomes with that? But this is all going to be navigated. But I see this as a positive thing, a new type of technology that we get to use. But like any technology, it also has challenges associated with it, and that's going to be another fascinating conversation to have within science and with society. But I can't think of anything that won't change. Even when I think, oh no, this won't change. Like no, probably will. Yeah. Do I see any other questions before we adjourn for more drinks and food? Yes.
So what I might be asking you like probably wrong or something, but because I don't work with jets a lot. But usually when experimentalists work with jets, there's like an angle that they define a jet with, I think also an energy that they define it with. So is it something that you give as an input to your model, or is it also something that it just runs on it?
Great. So the question was more technically about this field of jets and what information I provide to the machine, and how much do I tell the machine about the way that I process the information traditionally versus how much do I let the machine figure it out for itself. And this is also a fascinating spectrum. So on the one end of the spectrum, which is my curmudgeon-y days, I say, I've studied jets, I'm an expert on this, I want to inject all of my knowledge. And that forces the machine to respond in ways that correspond to what I already know. So I can't surprise me. On the other end of the spectrum is just throwing all the raw information, let the machine figure it out for itself. And from the Centaur scale that I showed you is precisely this question about where do you put the line? And so for the particular thing that you said, well, aren't jets already defined relative to an axis or whatnot? And so yes, that's the traditional way of doing it. Should I maintain that traditional way? Should I try a different way? And that's the conversation that we're having. There's a concept that's sometimes referred to as the kind of bitter lesson. The bitter lesson is that oftentimes the less domain knowledge that you put in, that is, the more you think about it as an abstract, generic problem, the better the machine does. And this is kind of frustrating for someone who spent their whole life studying these things and realizing that actually the generic-y solution is actually better than my custom solution. And that was indeed what we faced with when we were doing this topic modeling. It's like the generic treatment, like my data is not special. My data is no different than natural language. It's no different from there's a data set that is 3D renderings of furniture. So like 3D renderings of furniture, which is definitely not fundamental, versus quarks and gluons, they process them the same way. And that's the balance. And it's a constant negotiation about those things. And I don't think we've figured out the definitive answer to this, but that's why I like this example of the Centaur, and because it really is pointing out that there are two approaches and we need to find that right balance. Yeah. Do I see Okay, I think we are concluding the formal part of the evening. I look forward to more conversations with you informally. Thank you so much. Appreciate it.